Now it's time for us to move to our second talk. And our next keynote speaker is Dr. Jennifer Pett-Ridge, and she is a leading expert in soil microbiology and biogeochemistry. She authored the influential Roads to Removal study on achieving U.S. carbon neutrality by 2050. As a distinguished member of staff at Lawrence Livermore National Lab, she researches CO2 removal in agricultural soils using advanced techniques. She also holds adjunct faculty positions at UC Merced and UC Berkeley. Dr. Pett-Ridge's impactful research has garnered her over numerous awards and over 150 publications. So please help me welcome Dr. Pett-Ridge.
Well, good morning, everyone. Thank you so much. I'm so thrilled to be here, and largely because I'm here with a team of supporters, and I really want to bring all of you on board as well to tell you about a recent analysis that we published that follows on from what you just heard in terms of decarbonization and brings us fully to carbon neutrality. And this is the topic of carbon removal from our atmosphere. So our report, Roads to Removal, is something we put out last December. We have executive summaries in the back of the room here if you want to hear more after my talk. And a whole team of us are here that will be part of some panel discussions later in the day. So before I tell you the global picture, what I want to bring it down to is local. Global climate change and the effects of our changing weather systems are causing dramatic effects at a scale that I think is really hard for us as humans to take on board. So I wanted to talk a little about what's going on right here in North Carolina, and even more locally on a watershed that is kind of dear to me, and that's the Tar River. And if you know anything about what's happened in the past decade, we've had a number of events where hurricanes or huge weather systems have caused massive flooding on the Tar River. And that has disproportionately affected some of our most vulnerable communities, particularly in Princetonville, which is one of the historically Black communities in this area. And a good and dear, dear friend of mine leads an organization called the Tar River Land Conservancy. And this is not just an organization that's doing protection of wildlife and wildlands for the sort of aesthetic or biodiversity reasons. Those are critical. But because this land acts as a sponge. It's a sponge for CO2 that is drawn down via trees and their photosynthetic processes. It's also a sponge for clean water. And it allows our ecosystems that we live within to maintain a balance when we have these enormous physical energy effects of huge storms to prevent these drastic and negative consequences of flood events. So by protecting these forests and growing more and managing the forests that surround landscapes where we live, right here in North Carolina, we can actually have both effects that involve social justice, affect our climate and the carbon balance of our planet, and affect our water quality. So I wanted to tell you that local story before I'm going to now transition to a global and a national scale. You've just heard a wonderful description of how critical it is for us to decarbonize. And I'm glad that that word is a comfortable one for this audience. I hope it is, because it's the one that I use. And that is essentially getting us from where we are now to somewhere about 2050, where we achieve what we call net zero. But the reality is, even with all those wonderful advancements that you just heard about, we're unlikely to make it all the way to zero greenhouse gas emissions. North Carolina has cut a third. That's amazing. I expect that trend to continue here in this state and around the country, but we're just not going to be able to decarbonize particular industries. I'll point to sustainable airline fuel as one thorny issue. Producing steel and cement are some others. And agriculture is simply an area where we have nitrous oxide emissions, greenhouse gas emissions, that we just don't know how to completely get rid of. So we have to do the basic math to make up for the amount of carbon that we know we're going to still be emitting. And that's what we call negative emissions or carbon dioxide removal. This is literally taking CO2 from our atmosphere and storing it somewhere durably within our ecosystems or within geologic systems. And if you look at what the International Panel on Climate Change suggests, that globally we need to achieve something on the order of 10 gigatons, those are billion tons of removals per year by 2050. It's kind of just such a vast number, it's hard to really get your head around. But in the United States, our portion of that is essentially 1 billion tons. And that's what our Department of Energy has established, and the White House has established, as the goal for their carbon negative Earthshot. So how can we do this? Can we actually achieve 1 billion tons of removals? Well, that's what our report set out to answer. Why did we even go after this? Well, we had some experience in California, where I live, in assessing the amount of and types of removals, the capacity and costs just for our state. And so it wasn't such a big leap to think, well, maybe we can do it for the nation. It was certainly a bigger task. But that's the backstory, as it were, of Roads to Removal. This team that are here with me today are about 5 or 6 folks who are part of a larger group of 68 individuals who contributed. And I think you can see here just from the logos, they came from all across the country, different universities, different national laboratories and institutions that had expertise in a whole range of topics that I'll go through with you today. What I want to emphasize is that our analysis looked at what is our capacity? What are the costs going to be to try and pull 1 billion tons of CO2 out of our atmosphere by 2050? And fundamentally, just can we do it? Do we have the resources? Do we have the land available to make that goal? We really felt it was important to provide county level resolution. So high spatial resolution, because I said at the outside of my talk, things happen locally. The change, the new industries are going to happen with resources and demand for new jobs that are local, that have to do with what a county land manager, maybe even a mayor, might make in terms of decisions. We included a lot of cross-cutting analyses, and those range from environmental and equity justice, who's affected, who gets a new job, who doesn't, as well as land availability and the availability of renewable energy. And the last thing that I want to say before I start to dive into some data is this is not meant to be a policy recommendation. I'm an academic. I'm going to do my best to not be too academic as I'm speaking to you about these results, but the reality is I stay in that lane, and I thought it was important for our team to do that. The policy is the next step, and I hope that what I tell you about today does inspire all our lawmakers, but also our industry entrepreneurs to make change. But we've tried to simply present the data in as an unbiased way as we could. And lastly, on this slide, I'll just point, we have a wonderful website put together by colleagues at Climate Now and the Lawrence Livermore Foundation, and that's roads2removal.org. Some wonderful little videos, podcasts, fact sheets. You can scroll over what county you were born in and look at what the carbon removal potential of just that location is. So let me take sure that we're all on the same page on the different topics that we're incorporating within this report. So we start atmospheric CO2. The easiest way to pull that out of the atmosphere is plants. Plants, trees, grasses, crops are doing this naturally every day. They're efficient, and it happens for free for the most part. So we can look at cropland soil carbon or forest biomass carbon as one way to simply encourage removing CO2 from the atmosphere. The biomass from those forests, from those crops, can be collected, and a lot of it already is. Much of it is currently burned or allowed to decompose, but we could purposefully collect some of that biomass and move it into carbon capture and then storage of that carbon. And we call that technique bikers, or biomass carbon removal and storage. The acronym is not important. What I want you to take home, it's the carbon removal that we put first. Lots of times when we think about biomass, we think about burning it for energy production. We've got pellets going off to the Drac plant in the UK. But in this case, we're really trying to flip the story, as it were, and focus on carbon removal first and products second. We also, in the process of doing biomass carbon removal and storage or direct air capture, produce a concentrated CO2 stream, and we want to durably store that. And we can do that in geologic systems. There's some opportunity here in North Carolina, and we've mapped where the opportunity is throughout the country. We also need to, while we're thinking about these approaches, we want to think about the environmental justice effects on the communities that would both be part of these new industries, but are also in locations that have been disproportionately affected in the past by particularly the energy sector. So that's essentially laid out in pictorial form, the scope of our report. There are a number of different technologies that I'm not going to talk about today. And you may have heard of wonderful new ideas in enhanced rock weathering, or what we sometimes talk about as blue carbon management, the management of our coastal wetlands, or ocean alkalinity assessments. So all of those kinds of techniques that are currently in the R&D pipeline were not included. We only included mature technologies, things we know we can do today or that we could do by 2050. In a way, that means it's even more exciting because we really know that those technologies, some of them at least, will have come on board by the time we get 2 decades hence. But I'll just say that those that are in color here are what we really analyzed in detail in the report. So let me give you the answer. The answer is absolutely. Our country can achieve 1 billion metric tons of CO2 removals by the time we get to 2050. And I'll break it down for you, the different pathways that we need to do that. But the bottom line is that that can happen using the demonstrated technologies that we already have. It's going to cost on the order of $129 billion per year. And that's a big number. And I sometimes want to kind of unpack that with folks. Is that too much? Is it something that we can afford? Right now, that's about 0.5% of our GDP. But think about some other numbers. About 5% of our GDP is estimated to be a cost of our current pollution and fossil fuel related health effects. We've got $93 billion a year just last year caused by climate effects, essentially weather-related changes and dramatic destruction in communities around the nation. So these numbers, while large, are really in a way dwarfed by what we're already accepting in terms of the negative effects of how our climate is changing. I'll also just mention, what else can you buy for $130 a ton? Think about that. I think you can probably get some sand, maybe rock, but not much. So buying CO2 at $130 a ton is actually a bargain. And doing this is going to create an enormous number of new jobs, and we'll walk through that as I go through my talk. What I want to point out, though, is that what we need you for is really to get us from here to 2050. Sorry, I meant to go forward. We have opportunities in forest management and cropland soils that I'll talk about that we are ready to implement tomorrow. We absolutely know how to grow loblolly pine forests. We know how to do cover cropping. These are technologies that we have stakeholders who are ready to invest in. In some cases, you can even make money. But the reality is that per year, those approaches do not achieve the level of CO2 removals that we're going to need. We're going to need the more complex technologies, but like biomass carbon removal and storage and direct air capture. because those are able to really, really scale and get us to that 1 billion tons per year. But again, you got to be able to hold both things in your head, that even those natural solutions, those approaches where forests and cropland soils are being managed, if we start that today, the cumulative effect is enormous. And so we really need to invest in Mother Nature's ability to remove CO2 as we're building up the technologies. So here's our supply curve, all at once. And I recognize that the font may be a little small for you here, so let me just walk you through the colors, which is most important. So in green, we've got the amount of CO2 we can remove in our forests, and then in yellow in our soils. And this on the x-axis here is the million tons of CO2 per year, and it's scaled to that 1 billion removals per year level. And then we've got the cost on the vertical axis. And you can see that in forest removals, again, as I mentioned, you can potentially make money while removing CO2. It doesn't need to be a net drain. Soils removals tend to be very affordable, in most cases less than $50. But the big portion that you can see in this graph is in purple, and that's the biomass removal and carbon storage. There are many, many ways to do this. I'll walk you through them in a moment. But I'll say the biggest sort of and cheapest short-term approach is gasification to hydrogen. So collection of biomass waste and converting that to hydrogen while at the same time doing that CO2 capture. And I really should have said it the other way around, right? As I just said, CO2 capture is the first order of business. The hydrogen is a byproduct, but as you well know, it's a very valuable byproduct. This is green hydrogen that we heard about just in the previous talk. We also set aside a large amount of biomass conversion to sustainable airline fuel. This report was funded by the Department of Energy, and that is a national priority for our nation, that we need to have the millions, hundreds of millions of tons of airline fuel. And so while that's a more costly approach, we included it in our analysis. So then finally on the right-hand side, you're seeing DACs, or direct air capture and storage. This is using chemistry and essentially giant fans to remove CO2 from the atmosphere. You've probably heard about that. You've probably heard it's expensive. It is. But we'll show you that actually there are places within the country where it's really appropriate. Unfortunately, North Carolina and the Southeast region is not one of those, so I'm not going to spend a lot of time on it today. But I'll just mention that we analyzed the ability to collect CO2 via direct air capture all the way up to 14 billion tons per year. So this figure here could have extended a long way to the right. But it is more expensive, and again, as I mentioned, it's not something we're going to focus on for your region. So let me start with soils. The opportunity in soil management is largely focused on using what we call cover cropping, or having a second crop that's grown over the winter. Those plants are incorporating carbon into the ground. They're also having lots of benefits for water holding, for nutrient capacity of our soils. Right now, cover cropping is practiced on something like 5% across our nation. Most farmers, if you talk to them though, are happy to do cover cropping. They just don't always have the timing and the technology available to do it every year. I think that with moderate incentives, that could change. Perennial field borders and perennial carbon crops, this is essentially also planting grasses, trees that are around the edge of our fields that keep their roots in the ground for longer. Carbon crops like switchgrass have been grown in North Carolina for many, many years. And in those kinds of systems, you can actually harvest a biomass above ground to make a fuel while you're also putting deep, deep roots and putting carbon deep in the ground. So the map here is showing you those opportunities in green, the cover crops, the perennials and carbon crops in yellow, and the field borders in blue. And you can see the numbers of million tons we can remove are on the order of 130 to several hundred million. Largely that depends on how much we choose to pay farmers to carry out these practices. We don't expect anybody to do anything for free. So this will take investment, and depending on the amount we invest, you can see the returns. I've put on just the map of North Carolina there just to give you that kind of local flavor. Our thoughts are that largely the opportunity is in this coastal region, particularly on some of the more marginal lands, to be planting cover crops, and that could remove 1.7 million tons of CO2 by the time we get to 2050. Forests is a big, big opportunity. Forest management in this region, in the Southwest writ large, has been historically incredibly important. And I know that industry has had ups and downs. But what our analysis shows, and the lead author of this part of the analysis is here and would be happy to go into the details, is that there's an enormous opportunity in the Southeast to remove billions of tons of CO2 at a very affordable price. Here in North Carolina, that might be on the order of 200 million tons, both in the coastal and Piedmont regions. And there are two main ways that we are suggesting this could be done. Part of it is in simply restoring pine, largely pine plantations or pine forests that already existed, largely again on marginal lands that right now are not producing much in the way of row crops. The other is doing high rotation pine plantation, largely with loblolly pine, and using that biomass both for long live wood products that could be mass timber or different types of wood that are going to last for 100 years or more, or using some of that residue, that material for biomass carbon removal and storage, or what we call bikers. So let me talk a little bit more about that. There's carbon that is embodied in the stems of our trees and also all of the waste, those residues that are left behind, both in an agricultural system and a forestry system, also in our municipal systems. We produce a huge amount of green waste that we literally pay to truck to landfills. So if those kinds of biomass were used for carbon capture and the production of fuels or production of useful products, we could be removing on the order of 20 million tons of CO2 per year. It's an enormous opportunity, and particularly here in this region. So there are many, many ways that we can do this process that, again, we're calling bikers, but writ large across the country, it's the big win, 700 to 900 million tons. And we looked at a whole suite of different technologies, 27 different approaches. But I'll just point out the ones that I think are most impactful, particularly for this region. And that is, again, as I mentioned earlier, gasification to hydrogen while doing carbon capture, the production of biochar or carbon that is used then for polyethylene or plastics precursors. Small dimensional lumber is another way of saying mass timber. This is something we can be producing from even those fast-growing, fast-turnover forests like loblolly. And then finally, bio-oil is also in the picture. Bio-oil can be injected below ground and stored, or it can be used for other products like asphalt. Now, we have to make some decisions in how we use biomass and how we ran these numbers. So as I mentioned earlier, it was important that we worked with our colleagues at the DOE to think about the scenario where we take 500 million tons of our biomass and make sustainable airline fuel. But I'll just mention that if we don't do that, the maximum amount of carbon that we can remove at a price that's below $100 is really enormous, and that ranges all the way up to something like 700 million tons. So we're going to have to make decisions as a nation and as individual localities on how we choose to use our biomass. After you've done the biomass conversion and captured that CO2, it needs to be durably stored. And the biggest answer for durable CO2 storage is in our geologic storage basins across the country. And if you're not familiar with this technique, I want to make it clear that this is happening literally a mile and a half sometimes below the surface. This is injection of high pressure CO2 into formations that are often sandstones or saline aquifers where we have tiny, tiny grains that CO2 is being pushed down into. It's a safe, well-studied technique, and it has been mapped across the country already. The regions you look at here in green have really excellent geologic storage potential. The areas in yellow, we still need to do some more drilling, some more digging, as it were. But we show that in our report that the costs for not just injecting the CO2 in a well is quite affordable, but maintaining that site for the 20 or 30 years where we need to monitor to make sure that that things are staying safe. But again, this is a technique that's been used, that's been studied extensively. That said, we have a very slow process right now of approvals for the Class 6 wells that are needed to do this kind of injection. So as I mentioned, direct air capture is something that's been very exciting. It's captured the attention of a lot of entrepreneurs around the country and around the world. The use of chemistry to pull CO2 out of the air and then inject that below ground is exciting. It can ostensibly be done in anywhere, but in our analysis, we really restricted it to land where we didn't have other uses, where we didn't have forestry or agriculture or municipalities or any kind of protected land. And that really meant that we were focused mainly on the Intermountain West, where we also have lots of abundant renewable energy to drive this very energy expensive process. So again, it's very likely not going to be something that is a huge part of the sector here in the Southeast and in North Carolina. Now, as I wrap up, I want to point you to some of the cross-cutting analyses that we did. What are the effects on land and air and water and energy, but also on human health? And this is what we call our EEJ, or our Energy, Equity, and Environmental Justice Analysis. We looked at 26 different variables. I can't go through them all with you right now, but everything from social vulnerability, which has to do with health and people's take-home paycheck, to where we have opportunities to prevent soil erosion, to where we have opportunities to improve air or water quality, or change the amount of these forever chemicals that we call PFAS in our water and our air. And in that analysis, our lead author, Kim Mayfield, has mapped out here where we have the most opportunity with each carbon dioxide removal approach across the nation. And again, I'll just point you to North Carolina up at the top there. Lots of opportunities associated, again, with that Bikers approach or biomass carbon removal and storage. Largely, those are going to be having benefits for minority-owned farms, as well as for our air and water quality. We focused on taking waste from our CAFOs, or our essentially feedlots, which, as you know, there are many of here in the state, and using that waste for carbon capture. It helps both the climate writ large, but it also helps with local issues of water quality. So in wrapping up, I just want to point out this map of the United States where we really clustered the opportunities, and you can see here that not only is there county level variability in the opportunity to remove CO2 from the atmosphere, but there are regional opportunities. The answers in California will be very different than the answers and the policy that's needed here in North Carolina or the Southeast region. And that brings me back to this conversation about everything needs to be local. And I am excited to try and inspire you to have those local discussions with your community leaders, with entrepreneurs, and with policymakers, again, here in North Carolina and in the Southeast region. If I leave you with anything, it's with these few tenets here at the end. Mother Nature is important. Our forests and soil management is incredibly important, and we need to start affecting CO2 removal there today. But Mother Nature can't do it all on her own. So we need to value the biomass, those residues, those things that we call waste right now, for the carbon that they embody, and not just what they can do in terms of the electrons when they're burned. That carbon is incredibly valuable, and we can produce valuable products with that biomass. But we're going to need new R&D, we're going to need new tech to continue to move these technologies forward and to bring down that cost curve. And finally, if there's nothing else that it sticks in your mind, it's that there's no one solution. There's a mix and match approach that we're going to need, and across the nation, there are different opportunities and different costs and renewable energy availabilities. And so we need to take those on board. I know that that complexity can feel daunting, but again, let's think local, let's think what are the opportunities in this county and this region, and there are many. So I'm again going to thank the funders of this report, the Department of Energy, this amazing team that I was privileged to work with, and also the foundations that have been making it possible for us to come and give talks like this to groups like yours. Thank you.